Okay, welcome back. I hope you enjoyed your break. And I have, of course, started recording this video at exactly the wrong time. I'm going to be hangry before I finish recording. But anyway, now that this actually is like somewhat filled in, right? So video links here. I'll include just a note about how long the video is. Because I think during the premiere, you don't know when it's ending. Of course, if you just click a link later, you do. But yeah, they're all going to be right about 50 minutes, unless I really decide to knock off early. And then this is where I start because that's where I left off. Okay. What happened to my terminal? Okay. So yeah, talking about creating a pipeline, like how do you put these steps together into code? Maybe what you want is to be a little bit more interactive. And this can happen especially as you're sort of figuring things out, I guess. Like data cleaning is often a very interactive process because you realize like, oh no, there's data missing here or whatever. What am I going to do about that? Well, what if I do this? What if I do that? Or does this analysis do what I want? Yeah, okay. And you do want to sort of experiment, and that's totally reasonable. Maybe you have worked with Jupyter notebooks before specifically. Maybe you've worked with something else that is a notebook style. But if not, let's try that. So I have a terminal here. I'm going to work in Linux because I'm used to it. I don't care. You use whatever computer situation you want. I'm just going to, I have already installed all these things. I'm going to start Jupyter Notebook. And by install all these things, I do have on the course website, there's this collection of technical instructions. I've done this basically. Is that what I did? Yeah, like I installed Python-y things. I installed the Python libraries I need. If you're a UV user, fine, whatever package manager you like is fine by me. Okay. So when I started Jupyter Notebook, it opened up this thing in my browser. I'm going to start a new notebook. I am going to call it something better than untitled. Okay. So what's happening here is each one of these cells is effectively a little snippet of Python code, and I can write Python code here. So if my code produces output, I'll see the output. If my code returns something, like if the last thing here is an expression that has a return value or none return value, I will see that. It looks real similar, but of course, hopefully you know enough Python to know this is a string that was printed. This is the result of evaluating that expression. Those are different. The other thing that I literally felt my fingers do, and my brain didn't even know what was happening, is if I press enter here, I just get a new line, and I can have more than one line of code in here. But to actually make it run, I'm pressing Shift Enter. I've not invested in a top-down camera on the keyboard just for this one bit, so trust me. Shift Enter runs all the code in the cell. And once again, if the last thing that's there is an expression with a return value, you see it. If there's no return value, it just runs and you see nothing. So this, of course, then becomes a really easy way to experiment a little bit and say, oh, what if I change this? What if I change that? You can run one cell at a time. Yay. I'll ask for notebooks once in a while. Most of the time in this course, I'm asking for a Python file, like, open a text editor, open a.py file. I have no opinion about your text editor. If you think VS Code is a good text editor, that's fine. If you think whatever VI is a good text editor, fine. I'm not asking for notebooks very often, just because it's more of a pain. Like the TAs would hate me. And also because I've realized I don't like them. I think I have totally come around. So Joel Gress was one of the authors of one of those books I mentioned in the last hour. And actually, I do this. This will now be the thumbnail for this video because it's got people in it. Anyway, notebooks, like all of these things we do that we call software engineering or software development, break when it comes to Jupyter notebooks. And it's this kind of thing. And I think I agree with it. Whether you want to watch an hour conference talk, I think, and I see students do this all the time when it's like, you have this notebook that just goes on for screen after screen after screen. And it's very easy to get yourself in like this kind of situation where you've been doing like this experimenting down here and you've done whatever. And then you come back up here and this works, right? It doesn't look like this should work because I'm using a variable that's not defined above, but it is defined below. And I ran these cells out of order. And this is madness. This is now broken, right? Like if I now, so this is restart is like basically kill off this Python process. You lose all your local variables and stuff. Now what do I do? How can I run this code? And like knowing that I have to run these two, then go down here and run, and then that's like, if you're in a group project and your group member told you, oh, you just have to run cell 4, then go back up to cell 3, you need to fire this person from the group. You need to fire this person from the job. They're a crazy person. You should at least keep an eye on this. So this fast forward button here is clear everything and run from top to bottom. This should work, right? The fact that this doesn't work means I can reorder. Like I can move this cell up. I'm aware this is now insanity, but probably you should at least do that once in a while. But if you get to the point, like if you're defining functions, maybe this isn't the tool, right? Like if you get as far as like you have a lot of code and you are defining functions, probably what you want is a Python program, not a notebook, would be my advice. Notebooks are good for interactive experimenting. They're really, really bad software engineering tools. And once again, they're shiny. I get it. I totally get like, like sometimes at least Compute 120 is offered in Replit, which gives you a very similar kind of interface. I totally get it. It's way more friendly and way more approachable. You're a grown-up software developer now. Write programs most of the time. Once in a while, like you don't want there to be a manual step in your data analysis. But boy, sometimes humans are just better at what they do. And again, I've been in this situation where it was, hey, we have these individuals in the experiment, and this is just somebody asked me, like, hey, you do data stuff, can you help? Like, I have this 10,000 row spreadsheet. I don't want to process it manually. It's like, okay, like, the people in the study, like, if this goes up and this goes down, that means this. If this goes down and that goes up, that means this. What if they both go up? It shouldn't happen. If they both go up, just flag it. I'll have a look and try to figure it out. And that was, like the automated step got rid of 95% or something of the cases. So rather than having to go through a 10,000 line spreadsheet, they had to go through a much, much smaller number of weird cases that they maybe would delete. Maybe they would decide, I can see what's happening here because I'm an actual endocrinologist who knows what these things mean. Can happen. Like, again, you would like to avoid it. Like as a good, programmer, hopefully you automate things, but sometimes. Or again, maybe this case might have been, we could have automated the entire thing, but there were so many weirdos left that it was easier to just evaluate them by hand. It would have taken hours to write the code or minutes to just fix it. You make that judgment call. It's all well and good for me to lay this out, right? And to say, look, data analysis pipeline, this is how this goes. And this isn't necessarily how this goes, right? Because sometimes you end up with like, you've done a little bit of the data analysis and then you realize, oh crap, after this, I have to go and do a little more cleaning, or there's actually more data I needed. And the way you write the code isn't the way you've run the code or the order in which you run the code or whatever. Do your best. Like, understand that reality is more complex than anything that fits on a slide, and write a README file. That goes a long way. This like this kind of thing, just like numbering the things, because let me tell you, like there is data that I'm giving you for weekly exercise N that I have the code that generates that. And every damn semester I go and I look and I forget in what order I'm supposed to run the programs. And you would think I would take my own advice, but every semester I don't. Or again, if you have like common library code or you have some functions that are shared, maybe something like this. But you know, figure things out, have a README file or something that gives you a hint, you know, even when you come back in on Monday and have to fix it, start dealing with things again. Okay, what am I gonna do? Pull that over there. Okay, that ends there. All right. Let's start actually manipulating data in Python. I think like if you don't know anything about data stuff, but you know about Python, it seems like the wrong choice. Python is slow, asterisks, usually. It's bad at data in a way that I'll explain in a second, at least the core languages. But we choose it for data science anyway, and it ends up being a good idea. And when I say Python is bad at data, I mean this kind of thing. Like the built-in data structures are fine. Like if what you want to do is manipulate relatively small amounts of data in a like friendly to the programmer kind of way, great. Lists and dictionaries and sets that are built into Python, awesome. But the thing that actually happens in memory, hello, those who have taken 295 from me, I would hope that you would understand this is now an ugly data structure, that memory locality is bad. There's a lot more memory being used for it than you would for an analogous C array. Even these things, like as much as I've drawn this as the integer 10, well, it's a Python integer 10, which is bigger than just 64-bit thing. It's a really rough data structure, but luckily we don't have to use that data structure. We have other options. So NumPy is, I guess, the first step down this path. Basically, well, array, like if you use the word array and then you nod, like if I say array and you nod knowingly, you get that. Along with like if you're a C programmer, what you think of as an array, you get a lot more than that because you got a lot of like, well, methods, or a lot of functions and methods to actually let you work with them, which C would never give you. Oh my god, let's rip that off. I don't need this. This is all garbage. Okay. Okay, this is how we start. So this Python import is import this module, but don't call it that, call it this instead. That's taking its sweet time. No. Again, I think this is the not using this account very much. So this is like the sort of canonical way to create a NumPy array. What the hell's going on? Have I lost my kernel or something? Maybe this is a yeah, what the hell? Kill Jupiter and bring it back, maybe? Again, this fast forward button. Yeah, okay. There we go. So I'm creating a NumPy array. I'm doing it by feeding it a Python list with initial data. I mean, this is weird, right? I just finished saying that Python lists are like a relatively inefficient data structure. So I probably don't usually want to do it this way, but it does fit on a slide, so good enough. This creates, again, a list of, well, 64-bit signed integers. I do have to specify the type. And as a Python programmer, that feels a little weird, but what I'm getting is the C style thing, including the memory layout, right? So this is a nice efficient array in memory. It uses, you know, n times the size of this bytes in memory, plus maybe a little bit. I get the types I kind of expect. That of course have weird names sometimes. You know, the thing is called int underscore because int is a reserved keyword, so you can't use the word int as a like name of a thing. So int underscore, fine. I don't know. Again, I like these. I think these are pretty, I don't know, expected, right? Double precision floating point. Sure, that thing that you call a double in C or F64 in Rust or whatever. Great. You can just store arbitrary Python objects in these arrays. That's probably a little, you know, messier and slower, but you can do it if you need to. Yeah, so our arrays are sort of rectangular with whatever number of dimensions you need. You know, you're not probably in this course going to need a like 27-dimensional array, but it can be done. And by the way, I do find myself often doing this in a Jupyter notebook where it's like, I'm going to define a thing. And then if I just do that, I don't see any result. I have no idea what was in there. If you just sort of mention the variable name on the last line, you can see it. And maybe this is a temporary debugging thing. Maybe once you're confident, you get rid of it. But it is certainly a common pattern that, again, my fingers just sort of do without thinking of it sometimes. NumPy arrays have a number of dimensions. The type, like they know the type they hold, they're a fixed type. And the shape is like, how big are they on each dimension, right? So the shape is going to have this many elements, and it's how big is each axis. So I can go from 0 up to this -1, 0 up to that -1, if I want to index out of it. So I probably don't want to do this, right? I don't want to create the Python list just so I can initialize the efficient thing. That seems inefficient. There's a bunch of ways to get there. The Python, like, well, I guess if you know the Python range function, the NumPy a range is exactly analogous. It's go from here up to there -1. So it includes 6. It does not include 14. I do find myself looking for linspace once in a while. And this is a linear progression, right? So get from here to here in 11 steps as float 32. Yeah, I want 32-bit or 64-bit floats or whatever they are. If you want to do something like, you know, make some kind of visualization where you have sort of each pixel or whatever, or each block in the thing, well, maybe this is the X value for each block, right? You decide, well, I definitely have to go from 0 to 5, and I want there to be 55 steps in between. Well, that's the collection of inputs I want on the X-axis. Again, that definitely something I do, not never. You can ask for uninitialized memory. Probably don't do that. It's not like a modern processor finds it very hard to initialize a block of memory to zeros. Probably if you need an empty array, get to 1 with all zeros. NumPy is pretty happy with big arrays until I run out of memory. I have recorded this lecture in the past, by the way, and just added extra zeros as I was talking and run my computer out of memory and had to restart the hour. So a little cautious, I guess. There's a whole bunch of stuff. If, you know, this is the identity matrix in a linear algebra sense, yeah, sometimes you really want that. That's really handy. Sometimes you're doing some kind of Monte Carlo thing where you just need a bunch of random values. Yeah, great. There will be different random values every time I run that block. Super. What else we got? Empty identity. You know what? Again, more handy than you might think is a collection of zeros that is the same shape as this other array, or a collection of ones that's the same shape as this other array. It doesn't sound like you need it, but geez, it does come up. And, you know, there are all these other things. Do I care about these other arguments? I don't know. Yeah, I might have to fiddle with the type. I might want a collection of ones that's the same shape as this array, but actually it's integers instead of floats or whatever. I'm probably not going to sweat the memory layout of the array. Why would I override the shape anyway? Cool. But have a look at your documentation. Like, be comfortable looking at the reference documentation for your tools, whether it's NumPy or Pandas that I'm about to talk about, or your game engine or whatever. The reference docs contain useful information. ChatGPT may or may not. One thing, actually, as I say this, so this is pretty brand new NumPy stuff. The fact that there's a different, like, you can have arrays that live in the CPU or not, and they're sort of roughing in these things. I don't know if it actually works yet. This suggests that it doesn't, but anyway, there's no way the large language models know about this. The 6-year-old Stack Overflow answer doesn't know about this. I know about this because I read the reference docs. There's a lot of tricks is maybe not the word I want there. Tools, methods. They're generally whole array operations. Like, usually you don't work with a NumPy array by indexing out of it. I often have to, like, if I have to index an individual element out of a NumPy array or a Pandas data frame, I often have to look up the syntax for it because I almost never do it. And this is a rule for us as well. There's a few spots where you'll need loops, but in general, all of these things should be do this to my data, not for every row in my data, do this, and then do it for the next one and the next one and the next one. Let the tool do the work for you. So things like this, where I've got 2 arrays of like an appropriate size. And I guess they're of the same size, so this sort of thing is going to work. And I can do this. So this is an element by element, like, you know, add the top left corners to get the top left corner. The same is true for multiply. Again, if you have a linear algebra thought when I say this, don't have that thought just yet. This is element by element. This is 1 times 1 equals 1, 1 times 4 equals 4, 0 times whatever equals 0. There is a linear algebra multiplier. You just have to spell it differently. And you can also do scalar operations. So you can do things like, I want to add 100 to every element in this array, or sorry, multiply every element in this array by 100. It's really nice. Like, obviously there's a for loop here somewhere. I didn't write the for loop, and that's great. The code that I don't write is the best kind of code. So the 2 things I just did, which is the 2 arrays are the same shape, or it's an array and a number. Those are the things I know how to do off the top of my head. But there's special cases of these larger broadcasting rules that I think you should be aware exist. I don't know them off the top of my head, but these are the things like, you know, if I have a 10 by 10 by 10 by 10 by 10 array, and I try to add a vector of 10 elements to it, something is about to happen. Things are going to get stretched in some direction or another, and I can never remember how, because I almost never do it. But when I do it, it's nice to know that the concept is called broadcasting, I guess. You know, I have had to do this where it's, oh, okay, I have a 3-dimensional array and a 2-dimensional array that's the same size as a couple of those dimensions. And what I want to do is multiply everything down this strip by that thing in the other position. You can do that. Do I remember how to do it? No. There's a lot of really useful methods in there. I have an array. I want to add up everything. Or I want to add up everything along the rows or along the columns. That's really nice. Or I can do the same thing as a function call, like there's the method.sum or the function sum in the module. I have no preference between these two. I guess I'll say it that way. They do the same thing. I'm willing to bet they do it with the exact same performance. I'm willing to bet one's just a reference to the other. Whatever makes you happiest. But again, all of them have this property, right? That what they do is operate on the entire array. Am I gonna get, well, array manipulation routines? Why not? So you can broadcast manually if that's a thing you have to do. Or yeah, split an array up into a bunch of smaller arrays. But what I really want is I want to just like do math or whatever. Mathematical functions with automatic domain. Sure. Yeah, okay, great. I can take the log of every element in the array. That's great. I might want to do that. Maybe not today, but great. Is there a similar method? No. Okay, so that one I have to do as a function call, not a method. It just is what it is. I don't know what automatic domain is there. Anyway. So with just this, like with what you're given by NumPy, you can get a lot done. There's a lot of sort of, I want to do this, I want to do that, I want to make my array. And if you can, you should, right? If I want to do some arithmetic on every cell, what I should do is do the arithmetic with NumPy. It will be faster. If I really want to do an operation that is call a Python function on every element, that's np.vectorize. So what I've done here is I've turned this function, this is normal first year function, into a function that takes a NumPy array and calls this function on every element, producing an array of this type. I have to declare my type because NumPy has to plan, right? It has to know what to allocate. So I can do this. This is legal. This is also dumb. So I guess, right, so this is multiply each thing by 2 and add 1. Yeah, I did that. This is, and I can do this. And if I have something that's like super weird, or I really, really need some Python logic, or I need some other Python module that expects Python integers or floating points, I can do that. If I want to do this operation, I should do that. That's how I should actually do this thing. Or for that matter, I actually could do this. So I just said that this was a normal first year function that takes one number at a time, but Python being Python, I can put anything I want there. This is perfectly legal to do on a NumPy array. So it actually happens that the original function also works on NumPy arrays kind of by accident. But I would frankly much prefer that usually. Just let NumPy do the work. Again, small note, just because I was shocked when I saw this the first time. If you have a function that returns a pair, those values get split up into 2 arrays. You don't get an array of pairs. That came as a surprise to me. The one time I wanted to do it. I don't think I've ever had to do it since, but I did add this slide because it really confused me. So I feel like this NumPy vectorize function is named wrong, because if I say vectorize, that might put a thought in your head of like, my computer has a vector unit that does SIMD operations, and that is the opposite of what we're doing right here. This is call the Python function many times. This is effectively, you create a for loop that calls my function in the loop. It's way slower to do things that way. Is this my... No, okay. Okay, it is time for my demos. So these two Jupyter notebooks that are linked from the slides, I have already downloaded. Just as a few other things, these collection of other NumPy examples, just so we can see some stuff happen. I've created this just because I needed some data to work with. I reshaped it. So this is just a metadata change. I'm going to say this is probably really fast because it doesn't actually have to reallocate anything. But I create this two-dimensional array. So I can do a whole lot of things here. So I have a two-dimensional array. So when I index out of it, I have to give two values, like which thing do I want? And if I want element like, God, I can never do this. So this is row 2, column 3 is the 11. So row 0, 1, 2, column 0, 1, 2, 3. Yeah. And it's a NumPy integer because that's what's in that array. If I say a colon here, that means all of. So this is row 2, all of it. Or all of column 2, which is this column. Or this is actually, it's the Python slicing syntax. So I can say I want columns 2 through 4 minus 1. So columns 2 and 3. Or I want column 2 all the way to the end of the array. So the colon means all of, and if I put a bound on one side or the other, it narrows it in at the start or the end. Again, I very rarely do this. I think the only reason I tend to do things like this is like I need initial values or something. I want all the first values in whichever direction I'm kind of imagining this code going. But very rarely do I do this. Like I have to think about this, even this syntax is pretty simple because I never do it. Something you can do, because I can do operations on entire arrays. So I have this array. I don't know what if I get away with that font size, that'll be a little easier. So I can say, take every one of those things mod 3, get that. I can ask, are those things equal to 0 or not? And I get a true or false. And then if I have this Boolean array like this, I can use it to mask, to keep only the things where this array is true. So if I have a true here, I'll keep it, else throw it away. And that's also the square brackets. So this super annoys me about NumPy, and the same thing happens in Pandas. I can use the square brackets to index. I can also use the square brackets if I hand it an array, if I handed a Boolean array, I'm saying like keep the ones where this works or where this is true. So I've kept all the things that are divisible by 3 out of that array. This is a really compact way to say that, if nothing else, right? This is a really efficient way to express myself. It also is going to be fast. This is probably a good example of using np.vectorize. I would never do it for the 2 times n plus 1, but I might do it like this, right? Like, okay, this is not the best prime number checker in the world, but it is, I believe, correct. Does it get 2? Yeah, it does. Okay. Sorry. This is something I would really struggle. Like if I had to go through the things in the NumPy docs and write this logic, I would really struggle with it. But I can do it in a Python function real quick, and then I can vectorize that function. This is, like I said, that's probably a good use unless there's some prime detection thing built into NumPy that I don't know about. Then I can take a bunch of integers and I can ask, and I can keep the only ones where that function returns true. And that's pretty cool. And again, a relatively beautiful way to express that thought. I don't have to have the sort of source of the mask and the application of the mask be the same array. They just have to be the same shape, right? So this is create a bunch of Booleans from this array, but use it to mask this other array. That's rare. Usually, of course, you're operating on and looking at the same array, but you don't have to, I guess is my point. Oh, right, I have another notebook. Okay, let's get this started because it takes some time. I created this array. Again, it's just some data, don't care. What I want to do is it is a 10 row, 1,000 column array. I want to add up along the rows so I get my 10 row sums. I can spell it this way. I could, like, this is the code of someone who is a C programmer and is writing Python against their will. They really are determined to just keep writing C code, and if they have to spell it with Python syntax, they will begrudgingly do so. It's correct. Like, this does come up with the right values. Or I went looking. I went looking like, oh, what other ways are there to do this? This is kind of cool. It turns out, well, you can I can index a row out of an array, and then I could add it up. Okay, I could do that, and 10 times. Sure. Also gets me the right answer. It turns out, like, I don't know, any operator in NumPy has a reduce method that I can use to apply it to combine a bunch of values. I can do that. Something called apply along axis. Like, I was surprised how long this example got. All of these are correct. But what I want to do here is I want to sort of point out this time it. It's magic in a Jupyter notebook or another IPython context. So it's not Python, it's again magic for this context, but it's, hey, take this code, run it a bunch of times, tell me how long it takes. So on average, this took 2 microseconds. It ran at 1 million, or ran at 7 million times or something like that. I don't care about that. I care about, on average, how long did it take? So yeah, doing this kind of sum or that kind of sum are unsurprisingly very similar. This one is consistently a little faster, which does confuse me, but anyway. The NP reduce sum. This one is equally fast. I guess I'm not surprised. What is summing if not reducing with addition? I want to put the unit changes here. This is 1,000 times slower to write these loops. This is why I'm telling you you're not allowed to write loops in this course, because it's worse code, it's easier to get wrong, harder to find bugs in, and catastrophically slower. Like 1,000 times slower is a lot slower. And again, these other things where I'm like not using the NumPy stuff as well are slower. Let the tool do the job for you. It's good at it. It's fast at it. Awesome. The way you express a shape in NumPy is inconsistent, and this drives me insane. If I want to create an array of all zeros, I have to give the shape as a singular argument that is a tuple. If I want to reshape an array, I can give the new shape that way, but I can also give it as a list of different shapes, or different array dimensions, or separate arguments. If I want random numbers this way, I have to give the array dimensions as separate arguments. If I want it this way, I have to give it the dimensions as a single argument that's a tuple. This is super annoying and I hate it, but it is what it is. You can deal. So NumPy is good at its job, arrays. And that's great. I like arrays, or whatever you call them in your programming language. They're a useful data structure. It's nice to have them be sort of memory efficient and fast to work on and whatever. I like that it gives me these super high level methods and stuff. I don't want the manual. I want that. Yeah, okay. Dang, I should have kept my my tab open. Yeah. Where? Sorry. Yeah, there we go. Linear algebra things, right? I I like that I have this thing that does the tensor dot product, that I don't have to write that loop or whatever. That's great. You know, I don't know quite what a Kronecker product is, but boy, if I wanted to calculate it, calling cron of two arrays seems like probably a lot easier than writing the code myself. And this code is going to be faster and more robust and correct. And who knows what my code would be if I had to write whatever horror this operation is. That's great. But it's just arrays. There's a lot more in the world. Pandas is going to give us a lot more. The fundamental data type that Pandas gives us is a data frame. If you want to think about a table in a database, yeah, that. So basically, it's a column and a table. We call it series and data frame in Pandas just because. But you know, rows and columns, and each column has a title, and each row has data in a bunch of cells. That thing you have in your head. Pandas. In a Pandas data frame, the rows are labeled. If you happen to have used any other data frame tool, that's probably not the case in that one. It is relatively unique to Pandas, where basically every row has what is effectively in a database a primary key. If you don't know about databases, I forgive you. But if you know about databases, this is probably a very useful explanation. So let's get this imported back here. And once again, I don't think this is valuable. I don't think I've done anything here worth saving or distributing, or it was from the slides. So yeah, you use pandas a lot, so you typically import it as a short form. Well, there's a bunch of ways to create a data frame. This is one. They do display beautifully. I'll give that in a Jupyter notebook. So I've just done that. I've just expressed things as columns. I have a column value that has these four things and a column word that has those four things, and they have to be the same length because otherwise what does it do? So I get these labels just because pandas. So every row is labeled and it has this kind of identity, and the default thing it does is 0 up to n-1. I usually don't care about that index because I'm not going to index values, but it does weird stuff. I can do operations like this. So I could do something like, so add a column, right? So this is the way I talk about a column in a data frame. So I can talk about a series. I guess I should be saying series. So yeah, take everything in that series and multiply it by 2 and then add it back in as this new column array. Or I can do the same kind of masking operation where I can, well, again, I'll step through that code. Maybe that's worth it. So I can do, well, that by itself is just the column. Mod 2 is apply this operation to everything, apply this operation to everything. So now I have, well, which ones of these things are even and odd? And then I can use that to select. And part of the reason I've done this is I wanted to point out this is not a location. It really is a label, right? So this row disappeared, this row was kept, and it kept its label with it. So it's not just a position, which I think a really easy thing to think when you look at that. The thing that gets, again, I think it catches a lot of beginners out, is when you move data around and when you have two different data frames that you're going to kind of put together, join, if you will, everything is joined by the label or index. Again, label and index are synonyms here. Maybe I will, can I think I can just do this. Nope. Is there some way to do that anyway? how do I want to deal with this? So what I'm dealing with, like in my slides, I've created a raw series, which is legal. You can do it. It's a little weird. Like I wouldn't usually do things that way. So what I want to do is create a data frame with that stuff in it. I guess I can just do this, you know. Maybe I'm being dumb. I can create a data frame and tell it what its index is. Oh, right. I have to do it's this way. Probably. That's what I wanted. Okay. I know this is super exciting. All right, this is what I want to do. This was my goal. I've created this data frame. So instead of, like what I did back here was I gave a dictionary of column, colon, contents, things, which I could, and actually would have been easier back here. Here, I've given a two-dimensional list of lists. It could have been a two-dimensional NumPy array or something like that. I've specified the index because I feel like it. I've specified the column names because this doesn't have column names in it. But I get the same kind of result. Now, again, point being here, I have this data frame with labels 0, 1, 2, 3. I have this data frame with labels 2, 1, 0. But the content kind of corresponds by label. And this is the case you want. What I want to do here is work with the indexes if I can. So I'm going to create a new column in my original data frame that's going to be the one column that exists in this data frame. And it's going to work. And it's going to join on the primary key. It's going to join on the label or the index. So doing this is not a positional thing. It's not take row 0, put it in row 0. It's align things on these index values, and where one was missing, well, you have a missing value which is represented that way. It stands for not a number. So you can do that. I know I'm coming to time here. I want to look at a little bit more realistic example that I will pick up next week. So again, I've created this as a two-dimensional array with the names of the columns and the index, just because I felt like it. I gave the index a name, which then appears here. I know it's weird looking, and I totally get that people don't understand why this is on this line and this is on this line. It just is. This is the name of the column. This is the name of the index that's labeling each row. This index happens to have a name. But this is much more realistic data, and I can do things like, you know what, let's just do this before I finish. Look at how beautiful that is, right? What's population density? Well, it's population divided by area. And what beautiful, expressive, easy to get right, hard to get wrong code. If I had to write the for loop, you know, I have to do the thing. I have to make sure I get every row, and it's harder to read. This code is beautiful and expressive, and I like it. And this is why I like things like pandas. So I am now definitely out of time. So I will see you in the lab on Friday. So again, come on into Cecil on Friday. I'll be there with the TAs. We can talk. Well, we can talk about exercise 1, even though it's not due for another week, or talk about whatever you want to talk about. See ya.